Bismillah, assalamu alaikum. My name is Maya Taraouf. I'm glad to be a part of Artificial Intelligence and Big Data 20, which is taking place in particular circumstances due to COVID-19. Today, I will be presenting my humble work entitled Using Quantum Evolutionary Based Algorithm to Solve Materialist View Selection Problem. I'm a PhD student at LSI Laboratory in USDHB, Algeria. We start with a classic definition of a data warehouse, which is collection of data from various databases for the purpose of answering online analytical processing queries. These queries help decision makers to make right calls. We all know that a database can be large enough, but when we speak about data warehouses, the size can really be a problem, especially for query answering time. To deal with this problem, several approaches were proposed in each phase of constructing a data warehouse. We find, for instance, partitioning in the conceptual phase, indexing in the physical one, and views materialization for the logical phase, which is the matter of interest in our work. Multidimensional modeling categorizes data as being either facts with associated measures, usually numerical, or as being dimensions characterizing those facts, which are usually textual. In a multidimensional model, we find a fact table alongside with dimensions. This example studies the total sales of items bought by clients within malls. We note that the fact table contains every dimension's key alongside with the measure, which is the total sales. Here we take the example of the previous slide, which is a star schema that counts the total price of sales of a product P to a client C within a mall M. All that can be found at the view labeled PCM. We all know that decision making is all about aggregate results, such as counting the total sales of a product P within a mall M no matter to whom. Such information can be found at the view labeled POM. Here we have enumerated all possible views of the given example. We note that the number of all possible views is equal to 2 power the number of dimensions. We can say that there is a concept of dependency between views, since some views can be answered from other ones. Here we take an example. The view labeled PCO can be answered from the one labeled PCM, since it contains more details. To represent the dependency between all possible views, we use what we call a lattice structure. It is basically a DAG, or directed acyclic graph, representing the dependency between all possible views of a given star model. We all know the definition of a classical view, which is a named query, and the result of this query is not calculated until its execution. Well, unlike the simple view, the materialized view is a query pre-calculated and stocked physically into a table. It is obvious that the size of a materialized view is much less than the size of the whole raw data. Therefore, we can gain some time by answering queries from the materialized view instead of answering them from the data warehouse itself. But in return, we have to deal with space and maintenance problems, since when a view is materialized, it will occupy an additional storage space and it needs to be updated periodically to match the data in the original warehouse. Materializing all views is not possible due to two main reasons: the storage space and maintenance constraints. That leads us to the MVS problem, which is to choose among all views the set of ones that maximizes the benefit or the total processing cost when materialized. And of course, with respect to space or maintenance constraints, which cannot exceed a given threshold. For our work, we only consider space constraint. The MVS problem is an NP-hard problem, therefore we use meta-heuristics to solve it. In order to use the lattice for MVS problem, we had to add some weights to it. First, for every vertex, we added 3 weights: RV, the initial data scan cost, FV, query frequency, and the size of V, which is the storage space needed to materialize the view V itself. And for every edge leading from the view V to U, we added 1 weight, which is WQVU, the processing cost of the query U using V. Quantum evolutionary algorithm, or QEA, was originally inspired from quantum computing, which is the result of merging both computer science and quantum mechanics. QEA is a population-based algorithm. Instead of using solution vectors as individuals, QEA uses quantum vectors. Each quantum vector is a set of qubits, which is the smallest unit of information in quantum computing. These qubits carry the probability of being at state 0 or 1 through two complex numbers alpha and beta, verifying alpha squared plus beta squared equals 1. We now talk about quantum operators. First, we have measurement, or generation of solution vector from a quantum vector. The second operator is quantum interference. It means that we move all the qubits, or probabilities, with a specific rotation angle to match a value of a global or local best solution. The third operator is quantum mutation. Here we have two types of mutation. Interqubit, in which we change the ordering of random qubits of a quantum vector, and the intraQubit mutation, in which we exchange the numbers alpha and beta of the same qubit. Here we have the pseudocode of the QEAM algorithm we use to solve the MVS problem. First, we initialize a population of quantum vectors. Then we keep repeating these steps for each quantum vector until certain stop criteria is reached. For each quantum vector, we generate a solution using the measurement operator. Then we use quantum interference to move toward the best global. And finally, we apply qubit mutation with some probability. If no improvement has been made for more than 100 iterations, we create a different starting point by reinitializing the quantum vectors. The lattice is represented by a binary vector in which the value 1 means that the view is materialized and the value 0 is used otherwise. The given lattice can be represented by the following vector. The white nodes are not materialized, so we find the value 0 in the corresponding positions. So we have the position 1 and from position 4 to 8, whereas the gray nodes are materialized, hence the value 1 in the positions 2 and 3. We use the QEAM algorithm to solve the MVS problem under storage space constraint, where we try to find the set of views that minimizes the objective function or the total processing cost, under the constraint of not exceeding the threshold S when storing this set. We call the solutions violating the constraint infeasible solutions. One of the most commonly used methods to deal with this problem is to implement a penalty function, penalizing those infeasible solutions and ensuring that even if they have good fitness, they will not be highly evaluated among other solutions. In our work, no penalty function is used. Instead of that, we use repairing functions. So we keep dematerializing the smallest view in every iteration until the constraint is no more violated. In order to test the performance of the proposed QEAM algorithm, we chose to compare it to the greedy HRU of Hari-Narayan. For 5-dimensional lattice, QEAM finds better solutions for all thresholds except 70, 20, and 10%, in which HRU and QEAM find the same solution. As for the 6-dimension lattice, QEAM outperform HRU, and that is for all thresholds with no exception. To investigate further the performance of QEAM, we tested it against the genetic algorithm. To compare the two algorithms, we used statistic indicators such as minimum TPC, maximum TPC, and mean TPC. By observing the 5-dimensional lattice, we can notice that the QEAM algorithm outperforms the genetic algorithm for all thresholds. What seems to be the best solution found by GEA, or the genetic algorithm, also called the minimum TPC, is almost always the mean TPC of QEAM. That means that QEAM found that solution for every single run, since mean equals minimum equals maximum for all thresholds except 50 and 60%, as shown in the table. As for 6-dimensional lattice, The table shows that QEAM finds better solutions since its mean, minimum, and maximum TPC are better than the genetic algorithms, except for the thresholds 10 and 30%, where a genetic algorithm finds a similar minimum TPC. Finally, for 7-dimensional lattice, the supremacy of QEAM over genetic algorithm becomes very clear, since QEAM outperforms the genetic algorithm for all statistical indicators, minimum, maximum, and mean TPC, and that is for all thresholds, with no exception. This proves the scalability of QEM's solutions quality. To conclude, we have treated the MVS problem with storage space constraint. We have used the lattice structure to express the queries or the views dependencies. Since the MVS is an NP-hard problem, we have used, like the literature, the meta-heuristics to solve it. We used a quantum evolutionary inspired algorithm called QEAM to treat the MVS problem. Experimental results show the efficiency and the supremacy of QEAM compared to the HRU and to the genetic algorithm, which are usually used to solve the MVS problem. Thank you for your attention.